Now let's see what is Cayley table. You already know what is Cayley table, right? The concept of Cayley table is very simple. So if you have, for example, any structure, you can create Cayley table for any structure, remember. But we will, but we are interested in the properties of group. Let me tell you, in group theory, you have many structures, monoid, semi-group, groupoid, many structures you have. But the most interesting structure is group. Okay, so most of the time, we will study Cayley table of group. But you can create Cayley table for any structure, whatever you want, you can create Cayley table. So what is Cayley table? You already know. Cayley table means operation table. Okay, so for example, if your set is like this, true, comma, false, if this is your set, and let's assume that your operation is implication, then tell me what will be the Cayley table. For this, what will be the Cayley table? The Cayley table will be like this: true, comma, false, true, comma, false. Is this a group? Is this a group? Tell me. This is your operation. Is this a group? This is not a group, right? This does not have any identity element. This does not have any identity element. There is no identity element, so this is not a group. This is a semi, actually this is not associative also. So this is a groupoid. This is simply a groupoid. Okay, this is not even semi group. This is not even semi group because the implication is not associative. Okay, now you can notice the Cayley table. What it will look like? The Cayley table will be like this: true, true, star, true. This entry means true. True implies true. That is true. And this entry means true implies false. Remember, this entry means true implies false. So what is true implies false? That is false. And this entry means false implies true. This entry means false implies true. Always read from left to right. Okay, so this entry does not mean true implies false. This entry means false implies true. Okay, so this entry means false implies true. That means this is true. And this entry will be false implies false. This is true. So this is your Cayley table for this structure. So you can create Cayley table for any structure, but we are interested in group. So let's see the Cayley table for group. Okay, so this is the idea of Cayley table. In Cayley table, if you have X here, Y here, then this entry will be X star Y. Okay, let's move on. So this is the idea. If you have GI here, GJ here, then this entry will be GI star GJ. This is the idea of Cayley table. For example, this is your group. We have already seen this is a group under multiplication, and this will be the Cayley table. 1 iota minus 1 minus iota, 1 iota minus 1 minus iota. You already know this is a group. In the last class we have seen, and this is a abelian group. This is actually a abelian group. So you can notice, because it is abelian, so can you notice this is symmetry? This Cayley table is symmetric because it is abelian, so it is symmetric. Because remember, iota star minus 1, that is same as iota star minus 1. This is same as minus 1 star iota. This is same as minus 1 star iota, means this. So you can notice that this is same as this. So there is symmetry here because it is abelian group. Okay, so this is the multiplication table. This is the Cayley table of this group. Now, how will you find out? Tell me, from Cayley table, how will you find out identity element? Finding identity element from Cayley table, how will you find? So what is the idea? Remember, identity element basically means that its column and its row will be same as the header. Okay, so if you have this like A, B, C, D, something like this, then tell me, okay, if you have this type of situation, let's assume A is the identity element. Let's assume this is the identity element. Let's assume this is the identity element. Then what will happen? If this is the identity element, then what will happen? Then this row of the identity element is same as the header. So you will get this A, B, C, D, E. Similarly, the column of the identity element will be the same as header. So I can say this will be A, B, C, D, E. So if A is the identity element, then this will happen. So this is how you can find the identity element from Cayley table. How will you find commutative property from the Cayley table? Just check is it symmetric or not. If you want to find Cayley table commutative property, then just check symmetric. It simply means that symmetric. It simply means symmetric table. If you have a symmetric table, what I mean by symmetric table? Symmetric table means if you have A here, B here, then this entry should be same as this entry should be same as this entry. Okay, basically this entry means A star B. This entry should be same as B star A. These two entries should be same. So this is the idea. Just check whether this table is symmetric or not. Basically, it's like symmetric matrix. It's like symmetric matrix. Okay, so this type of situation. So just check whether this is symmetric or not. Means this is your diagonal. If this is your diagonal, let's assume that you have A, B, C, D, E, and here also A, B, C, D, E. Then you can notice here this is called diagonal. Okay, these entries, this is your diagonal. Okay, so this is the diagonal. Okay, this is known as diagonal. And symmetric means what should happen? That okay, the mirror images should be same. For example, remember this is C, this is the diagonal. Now you can notice C star A, this should be same as A star C. So this should be same. They should be same. Similarly, for example, D star B, for example, this D star B, this should be same as B star D. Okay, so they should be same. So it's like this. Okay, so basically this is your diagonal. Okay, and there should be some mirror image. Okay, so they should be same, they should be same. Anyway, this symmetric matrix you will study in the linear algebra. What is a symmetric matrix? Transpose of a matrix. Okay, so that you will study in the linear algebra. We don't care about it. So this is the idea. Now let's see properties of Cayley table. Let's check out. So what is property of Cayley table of group? This is important. I am saying property of Cayley table of group. This is important. So in some interesting properties you have in a Cayley table if you have a group. What are those interesting properties? The first interesting property is, so the Cayley table we create for finite group. Remember, the Cayley table is created for finite structures. This Cayley table, Cayley table is created for finite structure. Created for finite structures. Finite structures. Okay, only for finite structures we create Cayley table. Now I can say if you have a finite group, then what are the properties? These properties we have already seen. You can notice row and column of identity element is exactly same as header. This third property you already know. Row of identity element is exactly same as header. Column of identity element is exactly same as header. Another property you can notice that in a row, every element will appear exactly once. No element can appear twice. Okay, in Cayley table of group, one interesting thing you can see in Cayley table of group of a finite group, because we are interested only because Cayley table is created for finite structure. So in Cayley table of finite group, what will happen? No element in any row, no element can repeat. In any row, no element can repeat. No element can repeat. And the same thing you can do for in any column. The same thing I can say for in any column. In any column, no element can repeat. Because what will happen if there is repetition? Tell me, if there is repetition, this is the proof. The proof is like this. If there is repetition, can it happen that you have repetition? Like, is it possible that you can have a repetition? Is it possible that you have repetition? What is the problem if this happens? If this repetition happens, then what is the problem? Then it means B equal to C. Then it means B equal to C, right? Because you are saying that AB equal to AC. You are saying AB equal to AC. Now, because it is a group, because we are having a group, we are talking about group. So what can I do? I can say that so B equal to C. So this B will be equal to C. Yes or no? Is it clear? So but you can notice in the Cayley table, on the header we do not repeat element. On the header, this is the header. On the header you never repeat element. On the header we write the elements only one time. So you can notice that if this repeats, it means B equal to C. It means B equal to C. So remember, no element will repeat. Similarly, you can do for column. The same thing you can do for column. For example, if this happens, let's assume A here, C here. And if this happens, then what is the problem? If this happens, then what is the problem? Now here you can notice that AB is equal to CB, correct? Yes or no? Because this means AB, this means CB. So AB is equal to CB. Now, because it is a group, so you can do right cancellation. So I can say that A equal to C. So if these will repeat, then this A comma C will be same. So that's the point. So I'm saying that each element will appear. And now remember, no element can repeat two times. Then what it means? So no element can repeat two times. What it means? If I give you this and no element can repeat, let's assume A, B, C, D you have, and let's assume A, B, C, D you have. Now remember, no element can repeat. So if I put B here, I cannot put B here, right? Because no element can repeat. So I can put A here. Now, can I put B here? No, because element cannot repeat. I cannot put A here. So I can put maybe C here. I can put maybe D here. Can you notice that every element will appear exactly once? Every element of G is appearing exactly once because no element can repeat. So in every row, every element of G will be present exactly once in every row. In every column also, every element of G will be present exactly once. So these are the properties. Are these three properties clear? So every element will be appearing exactly once, not less than one, not more than one, exactly once in each row and in each column. Every row, every column is simply a permutation of all elements, means every element will appear exactly once. Okay, so very simple. So in every finite group, every row of Cayley table contains every element. It will contain every element exactly once. Like Sudoku. Yes, correct. Like Sudoku. Okay, let's move on. So tell me, is this a group? This is the question. Is it a group? Is G a group? Is G a group? Why this G is not a group? So the answer is no. The answer is no. Because you can notice this repetition is not, will never happen. Because this repetition can never happen. Okay, you can notice. So this is not a group. You can say this is not a group. Or you can say there is no identity element. So you can notice this identity element does not exist. You can simply say that identity element also does not exist. And you also know that this repetition can never happen. This repetition, for example, this repetition can never happen. So this is not a group. Let's move on. Is this a group? Tell me. Is this a group? So first let me just make sure it's like this. So your header is this. This is your header. EG1. Your header is EG1, G2, G3, G4, G5. EG1, G2, G3, G4, G5. Now tell me, is this a group? Is this a group? So what did you do? Why are you saying that this is a group? Why are you saying that this is a group? Tell me, why are you saying that this is a group? Remember one thing. Okay, so let me tell you this note. If you have Cayley table of group, okay, remember, if you have Cayley table of group, that implies no repetition in any row. That implies no repetition in any row, comma, any column. But this is only one way. This is not correct. Okay, only one way. Please note this. If you have Cayley table of group, then there will be no repetition in any row, any column. There will be no repetition. That is fine, very good. But if there is no repetition, it does not imply group. Okay, so take care. So find, okay, now you can notice that you have to find. First you tell me, is it closed? First you tell me, is it closed? Is it closed? Yes, this is closed. Is there, okay, is there any identity element? Do we have identity element? Yes, identity element is E. I can say identity element here, identity element is E. Okay, can I say every element has inverse? Can I say every element has inverse? See, identity element is E, because you can notice this this identity element row is same as the header. Identity element column is same as the header. So we have identity element. What can you say about inverse? So tell me, what is the inverse of E? The inverse of V will always be E. Okay, just find out. If I want to find out G in G1 inverse, then what should I look? Where should I look? Tell me. If I want to find G1 inverse, then where should I look? I should look here. I should look here. Okay, so you can notice G1 inverse is G1. Okay, next, if I want to find out G2 inverse, then where should I look? If I want to find G2 inverse, then I should look who will give E. So G2 inverse will be G2. G3 inverse will be G3. G4 inverse will be G4. G5 inverse will be G5. So G4 inverse will be G4 and G5 inverse will be G5. So yes, so inverse property is also there. We have inverse property. Can I say it is a group? Can I say it is a group? Associative property is remaining. Closure property done. Identity property done. Inverse property done. But associative property is remaining. And let me tell you, checking for associative property is not easy. Okay. So in this, you just check this. G1, G2, G3. For G1, G2, G3, you check associative property is there or not. Here, check G1, G2, G3. Associative property, do we have or not? Check this. G1, G2, G3. Check this. Do we have associative property? Can I say this is same as this? Are they same? They are not same. So associative property is not there. Do we have commutative property? Can I say this is commutative? Is this commutative? G5. I think this is commutative. I think this is symmetric. So this is commutative. So all the properties are satisfied, but associative property is not there. Okay. So you can notice. So this associative property we don't have. So I can say so not group. So not a group. All the properties we have, but associative property is not there. Commutative property is there. You can check. This is a symmetric table. This is your diagonal. This is your diagonal, and you can notice this is a symmetric table. This table is symmetric. You can check. G3, G, okay, so this G2, G3, G5. So this is a symmetric table. You can check. Now let me tell you, checking associative property is very hard. So in the GATE exam, they will not ask you this question. See, this big question they will not ask you. Don't worry. They will ask you small question. Okay, 2, 3 element, 3 or 4 element they will ask you. So checking for associative property is very hard. But I gave you this question because I want to tell you that this is only one way. Remember, I gave you this question because this is what I want to tell you, that Cayley table of group implies no repetition in any row in any column. But it is only one way. If there is no repetition, it does not mean it is group. So this point I wanted to make. To make this point, I have taken this question. This question will not come in the GATE exam because checking associative property is very hard. Okay, so in the GATE exam, if they give you, they will give a small table. Okay, checking associative property, checking associativity from Cayley table is very hard. Okay, it will take time. So So small questions will be there. So small Cayley table will be there. Will be given in questions. Okay. Anyway, let's move on. Just quickly tell me about this Cayley table. This is a small Cayley table. For this Cayley table, you quickly tell me. One thing actually you can do, one interesting thing you can do, if you want to check associativity, never check associativity with identity element. Okay, one thing you can do to check associativity, never check associativity with identity element. Okay, never include identity element. Why? Can anyone tell me why? Never include identity element. Because it will satisfy. Because for example, consider this EAB. Can I say this is same as this? Let us check. Are they same? Are they same? Let us check. Tell me, are they same? Yes, they will be same, because this EA will be A, so it will be AB. And this E with anything, this will be AB. So you don't have to involve E. So this can save you some time. So to check associativity, never include identity element. Never include identity element. Because if you include identity element, the associative property will be satisfied. If you include identity element, like for example, let's include identity element like this. If you include identity element, can I say this is same as this? Are they same? Tell me, are they same? Yes, this will be A, so this will be AB, and this will be B, so this will be AB. So if you involve identity element, there is no need. So this will save you some time. You can save some time. Yes or no? You don't have to include the identity element. This trick will save you some time because you don't have to include the identity element. So this will be AB, because anything with E, remember, anything with E, that will be AB. And here this will be B. So it will be AB equal to B. So this is the idea. Okay, so just understand this. To check associativity, never include identity element. Now here, let's come back to this question. Now tell me, here if you want to check associativity, then you don't include this identity. Do we have identity element here? First you tell me, what is the identity element? Tell me, what is the identity element? First you check, is there any identity element or not? Identity element is E, because you can notice this is same as the header. This header is same as this, and this is same as this. Okay, so this is the idea. So I can say identity element is E. What else? Now, if you want to check associative property, now don't take E. The remaining three elements you can take. So now check associative property. Still it will take a lot of time. Remember, still it will take a lot of time. Okay, so that is the reason in the GATE exam so far they have not asked associativity from the Cayley table. Like they will give you Cayley table and then they will ask you associativity. They have not done this so far because still it will take more time. Okay, so is it commutative or not? First you tell me, is this commutative? Is this symmetric? So let's check EABC, AECB. See, this second row is second row is same as second column. Third row is same as third column, BCEA. Fourth row is same as fourth column, CBAE. So this is commutative. Okay, remember, if you want to check commutative, then what to do? To check commutative, this is what you need to do. To check commutative, just do this. Just do this, that ith row should be same as, ith row should be exactly same as ith column. This is what you can do. This is the definition of symmetric. This is the definition of symmetric matrix. So ith row must be same as ith column. So here the first row is same as first column, second row is same as second column, third row is same as third column, fourth row is same as fourth column. So yes, this is commutative. What are the inverse? Can anyone tell me? What is the inverse of A? If you want to find inverse of A, just check for E. So inverse of A is A. What is inverse of B? Inverse of B will be B. What is inverse of C? Inverse of C will be C. And inverse of E will always be E. Okay, so we have inverse also. So inverse property is there. The question is asking inverse of AB. Can I say that is BA? This question is saying inverse of AB. What is inverse of AB? What is AB here? In this AB is C, right? So the question is asking C inverse. Yes, C inverse is C. So the question, this question, if you notice this last question, this is saying inverse of AB. Can I say that is BA? For this Cayley table, inverse of AB, is it BA? What is BA? BA is C. Yes, this is same as BA for this table. So all the properties we have, is it abelian? Yes, it is abelian. So yes, this is abelian.